Welcome to the fifth episode in a series for calculating pi on my Relay computer. Here's the journey so far. And it started with a challenge, to calculate pi to 20 decimals, but on my Relay computer, my basic, limited, electromechanical 8-bit Relay computer. Which means this isn't going to be a quick or easy task. But then I'm 4 episodes in, so clearly a glutton for punishment, and therefore, on with the goal. The precision of pi my computer needs to calculate. So, how far have I got? Well, I've settled on a binary-friendly infinite series for pi, the Bailey-Ballwine-Plouffe formula, or BBP for short. Tiny issue though, BBP produces pi in base 16, not decimal, but that's okay as we can convert between the two. And so I converted the BBP formula into high-level pseudocode, and then last episode I built up a shopping list of the functions needed, the things I'll need to code up from the basic operations of my Relay computer. In the last episode we also took a good long look at long addition and developed an approach for implementing it. Which is just lovely, except one pretty big issue though. My computer isn't Turing complete, and that means none of this, nada, is possible unless I do something about that pretty pronto. Before I do though, I keep mentioning Turing completeness but haven't really said what that is, why it's rather important for computing pi and why my Relay computer isn't. Well, if you're into your computing, then hopefully the name Turing rings a bell. We are of course talking of Alan Turing. There's really not much I can say here that'll do him justice, but if you're not familiar with his life and work, I can highly recommend the book Alan Turing The Enigma by Andrew Hodges, or if you have some popcorn handy, you might prefer the 2014 film The Imitation Game. For our purposes here though, colloquially speaking, something is said to be Turing complete if it can simulate a universal Turing machine. Yeah, thanks Paul. Define a term with another term, why don't you? Well, okay, let's take a brief look at a universal Turing machine. First, imagine a tape, which is divided into cells, and each cell can hold a single symbol of some finite alphabet. Next, we have a tape head, which can read and write symbols on the tape. The head can also move left or right along the tape, one cell at a time. For the purposes of the model, the tape is infinitely long, or rather, long enough that the head always has somewhere to move to. Next, there is a register that stores the current state of the machine, and finally there is a table of instructions which tell the machine what to do given the current state in the register and the symbol at the tape head. For example, an entry might say something like, if in state A, reading symbol 0, then write symbol 1, move left, and transition to state B. Genius, eh? No? Well, this simple machine is capable of implementing any computer algorithm. It's a general purpose computer. If your machine can simulate this, then your machine is also a general purpose computer. So how about my Relay machine? Well, let's take a look at its architecture diagram and compare. The memory is a tape. Finite in length for sure, but enough to perform complex calculations like pi. The position of the head is represented by the program counter, referencing a location in memory. From there, we can read values in memory, and in the architecture here, each value represents a single operation that we want the computer to perform, a coded instruction. After each operation, we either move on to the next location in memory, or we might even jump somewhere else in memory. Our tape head is read-only, however, but we also have the M register, which can point elsewhere in memory, almost like having a second head on the tape, and this one allows us to write and read the values in memory. For storing state, we have a finite number of registers. But we also have state in our 3 ALU condition registers and in the current coded instruction being performed. Finally, we have the instruction table, which in this architecture is baked into the machinery of the computer. So yep, the architecture here is indeed capable of simulating a Turing machine, and therefore can implement any computer algorithm even with its limited instruction list. And if you want to see how far you can push the envelope here, do a search for single instruction set computers. Even with one instruction, you can calculate pi if you're clever about it. But generally speaking, the more instructions you have available, the less work the programmer has to do. So what's the problem then? Well, the architecture is certainly Turing complete, but the ability to write values into memory isn't implemented yet in the actual physical Relay computer. It's missing some key instructions, and those are now the only things standing between my Relay computer and Turing completeness. Let's do something about that then. Here's our instruction set so far, and there's lots we can already do. Move 8, Move 16 and Set AB cover register manipulation. The ALU class provides some basic arithmetic and logic operations, and then the GoTo class provides branching operations. To be Turing complete though, there's two instruction classes missing: loading registers from memory and storing registers to memory. These are absolutely key to implementing the long addition routine from last episode, or, for that matter, anything beyond a pretty rudimentary program. Whilst we're at it, there's another instruction class that we need for the long add, the 16-bit XY increment. Let's take a closer look at those new instructions. The first job for implementing any instruction is classifying it, and it's the job of the decoder to tell them apart. And it does that by looking at the 5 most significant bits of the instruction, and from there it can follow a decision tree to decode which class the current instruction belongs to. So if our instruction starts 10010, then it's a load. If it starts 1011, then it's an increment XY. Another way to visualise this is with an instruction map like so. And if we add our 3 new classes to the map, we get the following. You can hopefully see here why you have to be a bit picky about what instructions to include. Indeed, 3/4 of the space here is given over to just 3 classes of instruction. We're particularly limited using 8-bit instructions, of course, but even with the larger instruction sets of modern computers, there's still these sort of trade-offs and design decisions to be made. Cool, okay, so after classification, we've got spare bits to use as parameters. And we start with the load instruction, which can read a value in memory and load it into register A, B, C or D. To indicate the target register, we set the last 2 bits like so. Note then we don't actually need bit 2 of the instruction, so it'll always be set to 0. Next up is the store instruction, which can take a value in register A, B, C or D and store it into memory. Just as with load, we use the last 2 bits to set the source register. And again, we don't need bit 2, so it'll always be set to 0. Last up, we have the 16-bit increment, which will take the value in the XY register and increase it by 1. There's not really any relevant options for this instruction, so we just zero out the remaining bits. With an instruction classified by the decoder, it's then down to the controller to operate the right control lines at the right time, thereby performing the requested operation. There's an important Turing machine distinction here, by the way. The instruction code held in memory is the symbol on the tape. It forms part of the machine state. Conversely, the Turing machine instruction list is implemented in hardware, hard-coded with wires and relays. Often terms like instruction get used interchangeably, but the list of instruction codes in memory, the program, are just bytes of data, numbers effectively. It's the decoder and controller that apply meaning to that data and operate the computer. The decoder is the what, the controller is the how. Okay, so how does the controller know when to do the how? Well, as we'll see next, there's a sequencer unit that provides the controller with a set of carefully crafted timing pulses. By the way, we're heading for a white background next, so mind your eyes if you're watching in the dark. Ready? Here we go. At the heart of the sequencer is a finite state machine, a counter if you like, which advances at every rise and fall of the clock signal. At each state it generates a pair of pulses. The S pulses last for the duration of each state. The S' pulses last twice as long, and therefore overlap the next S pulse. The usefulness of this might not be immediately obvious, but it will be in a moment, promise. You may have noticed that each instruction class has a number against it, either 8, 10, 12, 14 or 24, and that's the duration of the instruction, the cycle count. ALU operations, for example, can be completed within 8 cycles of the clock, and so the sequencer resets at a count of 8. Our new store and load instructions are 12 cycles, so reset here. And increment XY is 14 cycles, so resets here. Go to instructions are more complicated, so go the full 24 cycles. In each case though, it's the controller that's telling the sequencer when to reset via the abort lines, and the controller is deciding that based on the instruction class indicated by the decoder. So the sequencer outputs aren't immediately useful on their own, but the sequencer has more in store. It combines S and S' outputs to form a series of derived pulses, PA through to PT. And with these, the controller can operate the right lines at the right time. For example, let's look at pulses S and T at the bottom right here. And you can hopefully see how these could be used for copying values between registers. And indeed, these 2 pulses are used in branching instructions. The J register is selected on pulse S, and then optionally, if a jump is required, the program counter is loaded in pulse T. The reason for the overlapping pulses is so that a loaded register is stabilised before the source register is deselected. If we only used pulse T, you could have a case where the source register drops from the bus milliseconds before the destination register disconnected, thereby zeroing out the destination register. The overlap avoids the problem entirely and simplifies the relay computer design at the cost of increased clock cycles. Depending on the instruction cycle length, and therefore the currently set abort line, either all or a restricted set of pulses will be available to the controller. For our 12-cycle load and store, the controller will receive usable pulses A through G, plus J and K. We'd also get partial versions of pulse H, I, L and M, but we'd ignore those on 12-cycle instructions. Whereas for the 14-cycle increment XY, the controller will receive complete pulses A through M. For the 24-cycle GoTo instruction, the controller receives, and uses, all available pulses A through T. Right, so we know the instruction class and we've got our timing pulses. What does the controller do next? Well, as mentioned before, it's all about operating the right control lines at the right time. So we need some timing charts. And here's one I prepared earlier for the Move 16 instruction class. It's 10 cycles long, and so we can utilise sequence of pulses PA through PG. One thing common to all instructions is the fetch increment phase here. And three important things happen in this phase. Firstly, we need to read the current instruction in memory into the instruction register. Simultaneously, we also load the 16-bit incrementer from the program counter. Effectively, we're pulling double duty on the address bus here for two destinations interested in the program counter's value. Note again that the shapes of pulses A and B ensure we securely load the destination before taking the source off the bus. With steps 1 and 2 done, we can then select the incrementer onto the address bus and back over to the program counter, which will then be pointing at the next location in memory. What's key in instruction timing is bus availability, shown in green here. For Move 16, we need the address bus, but we can see Fetch Increment is using it until at least step 7. To avoid any crosstalk or corruption, we keep a 1-cycle gap between bus users, and so we do our 16-bit move from step 8 onwards. This is why Move 16 is 10-cycle compared to an 8-cycle instruction like Move 8. Move 8 transfers values using the data bus instead, which is available from step 5 onwards, and so we can perform the operation whilst the program counter is being incremented via the address bus. So what do our timing charts look like for the new instructions? Well, we know the fetch increment phase will be the same across all three classes, so we'll just diagram the unique parts, and for the load instruction, we first select register M onto the address bus, and then ask the memory unit to gate the stored value out onto the data bus. We can then load register A, B, C or D accordingly. Store is, as you might expect, the reverse. We select A, B, C or D onto the data bus, select the M register onto the address bus, and then ask the memory chip to connect with the B2M bus to memory line. With the buses stabilised, we can then trigger the memory write. Increment XY needs a two-step approach and is similar to the program counter increment. The incrementer is loaded from XY, and then XY is loaded from the incrementer. The secret behind all this is how the incrementer unit is implemented in hardware. It's actually a 16-bit half adder paired up with a 16-bit register, and that's how we can capture a value on the address bus, add one to it, and then later gate that value back onto the address bus. So with timing charts done, how does that translate through to hardware design? Well, let's take a look at the controller circuit diagrams, and apologies again, this is going to be another bright white background in 3, 2, 1. Here's the combined load and store circuit diagram. The class of instruction comes in from the decoder here and here, with store on the left and load on the right. Notably, the relay is powered from bit 2 of the instruction code here, and that disconnects everything below if bit 2 is set. Now we're expecting that bit 2 will always be 0 for load or store instructions, but it's good practice to wire things up this way to allow for future expansion. For example, we could create a load derivative that ends 100 and loads from somewhere else. I'm not sure where that somewhere else would be, but this way the circuit gets out of the way if not specifically activated. At some point, the sequencer will ask us to set the appropriate abort line, which it'll do via the chat lines here. Both store and load are 12-cycle instructions, so when activated we connect chat to abort 12. Next, we'll take in the sequencer pulses on the second row of relays. As before, by default, we're disconnected from the pulses if our instruction class isn't active. If we're performing a store, then the 3 relays on the left are active, and pulse J will go through to B2M and select M. Then pulse K will go through to memory write. If we're performing a load, then the 2 relays on the right are active, and pulse J goes through to select M and memory read via the relay below. The extra relay isolates memory read and select M from backfeeding, and again everything is designed to disconnect if not in use. Arguably, diodes could be used here instead, although you'd need to keep an eye on voltage drop and fan out and so on. Last up then is register selection, and for that we take bit 0 and 1 of the instruction code here. And then the bottom left relay handles selecting register A, B, C or D, and the bottom right relay handles loading of the same. That's it. That's all there is to store and load. Let's take a look at the 16-bit increment XY instruction. Similarly, the class of instruction comes in from the decoder here. And similarly, we disconnect from the outside world if the instruction code doesn't end in 0, 0, 0, 0. The sequencer will at some point request our abort choice via the chat line, which we route through to the abort 14 line. Next, we accept the sequencer pulses through the second row of relays here, and again by default we're disconnected from the pulses if our instruction isn't active, but otherwise we gate pulse F to select XY, and pulse G to load incrementer, and then later pulse H to select incrementer, and finally pulse I to load XY. And that's it for the increment XY instruction. Now, there's another hidden function in this circuit diagram, but I'll leave that for guesses in the comments on what it does and what instruction code it responds on. So that's the instruction circuit design, and from this of course we can create our controller PCB. This is the upper controller card, so named because it has a lower card counterpart that connects with this card, creating a sort of double card sandwich. But it's on the upper card here where the store, load and increment XY circuitry sits, alongside the existing set AB and A or U instructions. On the flip side of the card, there's not quite as much to look at. Mainly the ground plane, and then the strip looking a bit like a deformed dinosaur is a power plane providing 12 volts to the relays that need it. Okay, so I said earlier that the only thing between my relay computer and Turing completeness was load and store instructions, and actually that was a half-truth. The PCB you're looking at already exists in the computer. It's all there, it's just missing the store, load and increment relays. So all I actually have to do is solder those in, and then we're Turing complete. Let's get soldering. And so out comes the controller card. Then the upper card can be separated from the lower card. In hindsight, these are almost a little too well joined together, but after this last bit of soldering, these hopefully shouldn't need taking apart again. And it's soldering time. Now, if you enjoy the relaxing sights and sounds of soldering, I've uploaded the full 25 minutes of just that separately on my channel. But for this video, time's getting on, so let's multitask a bit while he's getting that soldering done. Now, I'll need a program to test the new instructions, and ideally something simple and short. Here's the Fibonacci program I've used in previous videos, and I'm editing it in my Relay Computer IDE, which you can play with at editor.relaycomputer.co.uk. I could of course just handcraft the instruction codes, but using my assembly language here makes it a lot easier to read and think about programming, but as we type you can see the instruction codes being assembled at the right, so it all amounts to the same outcome. The program is fairly simple, and it starts by setting register A to 1 and register B to 0. We then go into a loop where we copy B to C and A to B, and then add back to register A. Effectively that means at each iteration, register A gets the next Fibonacci number, and we keep going until the add causes a carry, or in other words, after we've calculated the largest Fibonacci number that'll fit in 8 bits, which is 233. The problem with this program is that it keeps overwriting the last result in register A, but now we've got our new store instruction, we can write these values into memory, so they'll be much easier to see. Let's modify the code. Firstly, I want to set up the M register to point somewhere in memory for where I'll write the series. I could choose anywhere as long as it's not going to overwrite the program, and here address 20 is well out of the way. Note here that the resulting instruction is actually a goto, configured to load M rather than J, and never take the branch. It's a handy way of getting values into registers when the value is more than set AB can take. At the beginning of each loop, register A will have the value I want to store, so we use the store instruction here. You can see at the right that creates opcode 98, which is our store A instruction. You can see that if we change to register B, C or D, it changes the opcode to 99, 9A and then 9B. Last job then is to bump the M register right before the loop to point at the next location in memory. We want to keep the A, B, C registers intact, so using the increment XY function is a handy choice here. First then, we copy M into XY, we can then use the IXY mnemonic to do the increment, and at the right we can see the correct opcode of B0 is added. Lastly, we need to copy XY back to M, and unfortunately we can see that causes an assembly error. And that's because Move16 doesn't support that combination. Instead then we can copy Y into M2 via the 8-bit move instruction, like so. That of course means we need to keep within the same memory page as we're ignoring X and M1, although we could copy that too, but here we'll save 8 cycles by skipping it. Right, that's the program complete, and looking at the right we have 19 bytes to load into the relay computer, so not too bad. Ideally though, we'd want to try the program quickly first before taking it to the relay computer, and so I created an emulator here. And you can see it's already got the program loaded into memory here, which means all I have to do is hit run and try it out. And there we go, the hex digits of the Fibonacci series in memory slot 20 onwards. I can also click on the later ones to check the decimal values, so 89, 144 and 233. Just as expected. My emulator also reckons this should take around 4 minutes 15 seconds at default clock speed to run on the relay computer. Well, let's find out. So we'll start by loading the program into memory, and for each byte I enter it on the switches here and then push the deposit next switch, which will put it into memory and advance the program counter. I can now repeat that for the whole program. Here goes. Right, that's loaded in, so we're ready to run. First I need to prime the sequencer, like so. And with that done, I can set the computer running. Okay, that ding means our result should be sat in memory, so let's set the program counter to location 20. Cool, that's a 1. 1, 2, 3, 5, 8, 0D, which is 13 in decimal, and then in hex we have 15, 22, 37, 59, 90, and finally E9. Superb. And I'm not sure how impressive you found all that, but seriously, that's a major milestone complete for my relay computer. It's now Turing complete, and I know it can definitely calculate pi, even if I don't know how to just yet. It'll just be a matter of runtime and reliability now, and that's where I'll finish out this episode, I think. In the next episode, I'll code up the long addition routine and give that a run on the relay computer too. I'm off to celebrate a bit now, so all that remains is for me to say, as always, thanks for watching, and I'll see you next time.